Hello, my name is Bob D. Hilster, and I am your particle model guru. Today's video is on measuring the mass of the electron, and this is part one. There will be a part two. If you are new to the particle model, I suggest you watch these two videos, the particle model overview and levels of the universe. You will find links to these in the description of this video. Watch them to get a better idea because I don't always cover everything in any given video. Okay, the video I'm going to review today was published on July 12th of 2015, but it's really much older than that. It was republished by YouTube. The title is actually Calculating an Electron's Mass, and this is the link to that video. So I would suggest, if you haven't watched this one, which you probably haven't, you can stop right now, copy this video link into and watch it, or you can just continue to follow me. So assuming you have watched it, let's move on. This is the apparatus that they used, that the lady in the video used to measure and calculate the value of the mass of the electron. What we have here is a power supply. Back behind the power supply, there's a voltmeter up here, and there's an amp meter here measuring volts, measuring current. These are two big coils to generate a magnetic field using the current supplied to it, and inside is a globe. Okay, there's a globe, and that globe contains a little bit of hydrogen. And there's an electron gun and a deflecting plates back here. And this is the apparatus that is used to go to measure certain things and then calculate the value of the mass of the electron. By the way, it also calculates the velocity. Now this is a closer look at the electron gun, shooting electrons straight up, and two deflecting plates. These are electrostatic plates that are powered by that voltage, a DC voltage, and the DC voltage is measured by the DC voltmeter that I mentioned earlier. So the electrons generally shoot straight up, and the deflecting plates here are going to move the beam to the left or to the right. And here's a picture of one of the start of the process. As the electrons move up in this slide, you can see it because of the interaction of the electron with the hydrogen gas. And you can see there's a deflecting plate here and a deflecting plate here. The voltage across those plates are measured here. That's literally the volts across that plate, causing the particle to go straight up or slightly to the right. And this is the current meter measuring amps for that's measuring the amount of current through both coils. And when they get everything adjusted right, when they adjust the magnetic field correctly and the voltage on the plates correctly, they can actually make this electron move in a circle, like it was orbiting something. And yet we know that it's being controlled by the electric field here in terms of its initial velocity and direction. And we know that the magnetic field is causing this, because if you watch the video, you can actually watch them go from this slide to that one. Okay, and then they leave this in a static position and they take a picture of it. Okay, and they also take a picture. They remove the globe from the test setup and they hang a meter stick such that the 0 point of the meter stick is at the same height and distance into the globe area where the globe was. They hang that and take a picture of it. Well, now they have two pictures. When they develop the picture, they cut part of the picture away so they can lay the meter stick on top of the picture of the circle that the electron, and they can measure now the distance, the diameter of this circle. Okay, so this is the data they have. They have voltage to the plates, they have current through the coils, and they made a chart. I'm not showing that here, but they're able to convert the current through the coils into the strength of the magnetic field. And they also have the diameter of the circle. So they're going to develop two equations. And those two equations have two unknowns. They have mass and velocity. And they're going to develop two equations such that they can solve with simple algebra the values of mass and velocity. So I'm going to go through this a bit. I'm not going to explain the derivation of any. I'm just going to explain what this equation is first. Then I'm going to explain this equation as it's changed to that. This is the equation for the energy of moving an object m at velocity v. This is energy. Volts times charge is also energy, but this is electrical energy. This is mechanical energy. So you're setting energy equal to energy. Same thing here. This is force, not energy. This is the force. If you divide the distance r, which is the radius of the circle, into velocity squared, you actually get acceleration. Velocity squared is meters squared per second squared, and you cancel out the meter. One of the meters, you get meters per second squared, which is acceleration. Mass times acceleration is force. This is the mechanical version of force. This is the magnetic version of force. The magnetic field, the charge on a field, and the velocity of the charge. So they're mixing it. They're mixing mechanical properties of the electron with the electrical, in particular the electrostatic properties of the electron. Here they're mixing the mechanical properties of force with the magnetic properties. This equation is well, my point there was that they're mixing things up. It's not like they have electrical to electrical and magnetic to magnetic. They have developed over the years ways of converting mechanical energy or joules into electrical energy or joules, and they have these ways of doing it. This equation gets changed. They cancel out this velocity with one of the velocities over here, and they move r over to the right, and you get mv, which now looks like momentum equal to the magnetic field times the charge times the radius of the circle. And you can see here in this slide, they've already started to calculate or put into place the fact that they have 100 volts in the on the plates. So now this is a lot of stuff here, but here's those equations again, and there's the 100 volts, the charge of one electron. There's only one of them, and the answer is in joules. This is supposedly in joules. And this equation, they read off the chart the value of BQ actually, which is 0.97 times 10 to the minus 22. And there's only one charge, and the distance they measured was 11 centimeters, and half of 11 for the radius is 0.055, and end up with kilogram meters per second. Kilogram meters per second here, and kilogram, this is equivalent to kilogram meters per second here. So they have this term in mass and velocity with this value, and they have this term with mass and velocity with this value, and do a calculation. If you do the math, you end up with the mass of the electron being 0.89 times 10 to the minus 30th kilograms, and its velocity is 6 times 10 to the 6 meters per second. Values of the mass and the speed. So let's compare what they had back then in the past and what they have today. This is the number that was on the board, 0.89 times 10 to the E means exponent, 10 to the minus 30th. If you multiply this by 10, you have to divide this by 10. So multiplying 0.89 by 10, you get 8.9 times 10 to the minus 31. This becomes minus 31. Today, if you look it up, it's 9.1 times 10 to the E to the minus 31. Pretty close. So presumably they have better techniques today and they get a better answer, but at least when you compare what they did in the past to what they do today, the lady did pretty well. Now the speed of the electron is in meters per second. In the past, this particular experiment got 6 times 10 to the 6th meters per second. And today, well, this is not what the speed of the electron would be in this case necessarily. This is the speed of light, 3 times 10 to the 8th meters per second. So I'm comparing what she measured to the speed of light. I don't know what you would measure in this case today for that specific experiment. So this is the speed of light, which means that this value is 2% of the speed of light in the vacuum. So they're saying that in this case, the electron is moving at 2% of the speed of light, which is fast, but it's not as fast as you might think. You might think it should be moving at the speed of light. Well, in the particle model, this doesn't really work out very well that way. G1 mass, the mass of the G1, if you remember, the G1 particle replaces the electron, and it has no charge. But they're saying the G1 mass is in kilograms, and that's wrong. The G1 mass applies only to objects starting with atoms and molecules and larger. It just doesn't work. You can't measure, according to the particle model, you can't measure G1 in kilograms. So the particle model assumes that G1 is the electron. G1 gravity cannot act gravitationally with another G1. They bounce off of each other and scatter. That's chaotic motion. Gravitational motion is organized, is an organized force and is seen by the organized motion that occurs. A trajectory being shot on the Earth at 45 degrees and then falling back to the Earth. This is a very well organized force. It's the Newtonian force of gravity. But when a G1 particle interacts with the G1 particle, it scatters and you don't get organized motion. And if you saw in the video, you saw that it was they were able with this experiment to cause the particle, the electron, to move in a very organized way. Now, it actually turns out that G2 gravity applies an organized force on the G1 and the N1. G1 and N1. N1 is the nucleon, G1 is like the electron, and that's how we make these atoms and molecules. And G2 can cause the organized motion of the G1 or the electron. So that's the difference. They're measuring it in kilograms. They're mixing up mechanical equations with electrical, and they're mixing up mechanical equations with magnetic. And they get an answer in kilograms, and the particle model says, no, that's not right. The way you do that is with G2 gravity. Okay, looking at the speed of the circuit, this is an interesting point. The speed in the experiment was 2%, 1/50th of the speed of light. I got this from Wikipedia. The speed of the electron in a circuit, in this case, we're going to cover a circuit, has multiple meanings. In everyday electrical and electronic devices, the signals, this is the signals that are propagating in a circuit. Signals, they call it energy or electromagnetic waves. I'll stick with the term signals because as an electrical engineer, I traced many signals through a circuit. They typically have a speed on the order of 50% to 99% of the speed of light. Some of them go in the circuit at almost exactly the speed of light. Imagine that in a circuit that it's going at the speed of light. If it is going at the speed of light, it's probably moving in a straight line, precise straight line with not much deviation. Somehow, when they measured this value, it was probably a very small circuit, going a very short distance and going perfectly straight. And therefore, it's at 99%. But what about this one? What about the 50%? Why would the signal propagate at 50% when the speed can be as high as the speed of light? My contention is that when this circuit was probably more complex, there were more paths, more turns, and the path it took was not a straight line path. If it's not a straight line path, then the path length is longer than the straight line path. And if it's twice as long as a straight line path, you're going to measure signals that are as slow as 50%. My point being is that even when you measure signals moving at 50%, the G1 particle speed in the circuit is moving at speed c. It's only the path that gets longer. I don't know whether that's the case in this experiment, whether the particles are moving in a longer path than they say, and that's why the speed is slower. It's 2%. It's not half, it's 1/50th. It's quite slow. And that's a different point that needs to be covered at some point. how slow does it move? Do they say this is how they slow the electron is in a circuit? Well, there's an equation that's in that same reference, a Wikipedia reference, that says the speed of the electron is proportional to the square of the frequency. And then they give the example of a 60 hertz waveform going through the circuit, and its speed is 3.2 meters per second. Extremely slow. The electron moving that slow in a circuit doesn't make sense to me. To me, the G1 particle or electrons moving at speed c, this is just an equation. This isn't a measurement. This is somebody's equation. It's more complicated than this. You need to go look it up if you're interested. But the higher the frequency, the higher the speed. The speed of the signals, supposedly, but this is this is the speed of the electron. It's confusing, how fast are these things? The particle model, I contend, says that the speed of the G1 particle, the individual particle, is the speed of light, or nearly so. And so the speed of the signal depends on the path it takes. It doesn't always take a straight line path. In fact, if you watch my video on the left-hand rule and the right-hand rule, I contend that the particle moves in a spiral shape. Let me do that again. It moves in a spiral shape. Let me get this. It goes around in a circle as it comes closer and closer to you. So the path is longer, but the speed of the particle is the same. Okay, I already covered that slide. My next video will discuss the same experiment, but I'll use a particle model to explain what's happening. So if you didn't watch it, get this, copy down this link and watch this lady perform this experiment. I'm going to explain how it actually works according to the particle model. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.